Hey, welcome back. In this video, we're going to talk about the graphs of tangent of x and cotangent of x. We're going to give some reasoning for these graphs, talk about the periodic nature of them. So let's start by reminding us of the definitions of tangent and cotangent in terms of points on the unit circle, which I always feel is the best way to think about these functions. So if we're given an angle, and let's do this in terms of radians, which will be the way we really attack these moving forward. Given a certain angle, the tangent is the division or the ratio of the y and x values of the point on the unit circle. Cotangent is very similar. The cotangent is just the reciprocal of x over y. Given the fact that both tangent and cotangent are these quotients of the x and y values, let's get a quick visual of the unit circle just to investigate where the most obvious things are occurring for these two functions right here. And actually, it's going to occur at these easily known points around the unit circle. So we have at 0, this is also 2 pi. At pi over 2, pi and 1.5 pi's are 3 pi over 2. These are the most interesting for this conversation because we have these zeros. First of all, this point right here is pretty clearly, so this is the point 1, 0. This is the point 0, 1. This is the point -1, 0. And this is the point 0, -1. Importantly right here, the first thing to talk about is that when the numerator of this ratio right here is 0, the output will be 0. So the statement is whenever the y value is 0, tangent will be 0 also. And graphically speaking, those will be those x-intercepts or the zeros of this function. So in this case right here, y is 0 was whenever we're at one of these 2 points right here. So just to make this statement right here, so tangent will be 0 at these multiples of pi. So let's just go from a -pi, 0, pi, 2 pi. So any multiple of pi, the tangent will be 0. When we have the cases when we're at the odd pi's over 2's right here, this is where we get a 0 for the x value, which means this function is undefined. And so importantly, tangent is undefined at these odd multiples. And let's start from the negative, and you'll see the reason here in a second. -pi over 2, pi over 2, 3 pi over 2. And again, any odd multiple of pi over 2. And beautifully, since cotangent is just the reciprocal of tangent, we can actually take that information and just swap it for this conversation right here. So when our x value is 0 is when this was undefined, but it's when cotangent will be 0. So in this case right here, cotangent will be 0 at these x values that are the odd multiples of pi over 2. And then in the other same way, where the tangent was 0, the cotangent will be undefined because instead of having a 0 in the numerator, we'll have a 0 in the denominator. And so it will be undefined at these multiples of pi. And we'll go -pi, 0, pi, and 2 pi. So then to investigate the behavior of tangent. So importantly here in this conversation, I kind of hinted at this with talking about -pi over 2. I want to think about this point right here as -pi over 2 because I want to investigate the behavior of tangent in between its asymptotes. And importantly, when I'm talking about the first period of any function that we're talking about with these trigonometric functions, it's important to include 0. So while I could have gone from pi over 2 to 3 pi over 2, that doesn't include this input value of 0. So when I'm going to investigate the first period for tangent, or what I consider kind of like that first period for tangent, I'm going to think about from -pi over 2 through 0 to pi over 2. And again, at pi over 2 and at -pi over 2, I have these undefined values for tangent, which are going to translate to these asymptotes. And what I want to look at is what happens. So I know that tangent is 0 at 0, and then I have these asymptotes. So what is the behavior? And hopefully you'll see this when we go to the graphical representation of this. The question is, I know an asymptote exists at these x values, but what's the asymptotic behavior? Is it a positive asymptotic behavior or a negative asymptotic behavior? And to investigate this, what I'll do is look at a point close to these right here. And so first, let's look at this right here. I'll call this will be pi over 3. We know that this is 1/2, √3 over 2. So this will help us think about is as we go from 0 and approach this asymptote at pi over 2, what's the general value of tangent? And in the same way, we'll take, using this as a reference, we'll look at negative pi over 3, which is just here beyond negative pi over 2. I know these coordinates are exactly the same as this, except our y value is negative. So again, what I'm looking to analyze is as I go from negative pi over 2 to pi over 2 in this direction with increasing the angle, what's happening to my tangent? First of all, I know that the tangent of negative pi over 2 down here is undefined. That will be a vertical asymptote. I know here the tangent of 0 equals 0, and then I know that the tangent at pi over 2 is undefined. Well, then using this point right here at pi over 3, I know these coordinates, and I know the definition of sine, and maybe we know this, but remind ourselves, is that the tangent of pi over 3 is the y value of root 3 over 2 divided by the x value here of 1/2. And I won't show all the work for this, but dividing by 1/2 is the same thing as multiplying by 2, and that 2 will cancel this right here. So the tangent of pi over 3 reduces down to the square root of 3. And then investigating the same action down here, if I'm looking at the tangent of negative pi over 3, I divide these from each other and it'll look almost identical to the work I did up there. So root 3 over 2 divided by 1/2. This will be the same with the exception that this is negative square root of 3. And so again, what I'm trying to illustrate here is as I increase my angle, starting at negative pi over 2 where tangent is undefined, and then I increase, I know more a bit about the nature of the tangent function. We're undefined, then we're negative. By the way, this is going to mean as we approach this asymptote right here, we're going to approach it with a negative asymptotic behavior. Then we go to 0. Then our tangent value is positive as we approach this other undefined or horizontal or vertical, asymptote. So if we plot the information that we just investigated on a rectangular coordinate system right here, we see that we have this vertical asymptote at negative pi over 2. We have this asymptote at pi over 2. Then at negative pi over 3, we have this negative y value. At 0, we have a value of 0. And then at positive pi over 3, we have this positive value. And importantly here then, if we want to create a sketch of tangent, we actually have all the information we need. If we go from this 0 right here at 0 and tend towards that pi over 3, the only option we have in reacting to that asymptote at pi over 2 is to go unbounded in the positive direction. And again, we can't curve down and go back through the x-axis to have negative asymptotic behavior because there's no 0. The only 0 on this interval right here between negative pi over 2 and pi over 2 is that 0 at x equals 0. So as we approach that right asymptote at pi over 2, we have positive asymptotic behavior. And then if we go to the left, we have to go down to that negative square root of 3, and that will take us down to the negative asymptotic or unbounded behavior at that asymptote at negative pi over 2. And then importantly, we won't give the deep reasoning for this argument right here, but if we went between pi over 2 and 3 pi over 2, we actually have exactly the same nature of tangent on that interval right there. And actually that gives us a really important understanding about the nature of tangent, is that tangent has a period of pi. This is different than the other trig functions that we looked at so far. Every other trig function had a period of 2 pi because of one trip around the unit circle. But because the tangent isn't relying on just one of those coordinates, but it's the ratio or the quotient of these coordinates around the unit circle, that nature gives the period for tangent to be just pi. Looking at this also, let's look at the domain. So the domain of this function is all real numbers, except we're restricted by these values that make the denominator 0 at these odd multiples of pi over 2. So at all real numbers except odd multiples of pi over 2. And then also importantly for this trig function tangent, unlike the restrictions for sine, cosine, secant, and cosecant, where we had these different ranges, actually, as you can see, is as tangent approaches these asymptotes, it goes on forever. So there's any positive, any negative value, and there's no breaks within these little bits between these asymptotes. And so actually, the range of tangent is all real numbers, or from negative infinity to infinity. And then using exactly the same type of argument, along with the fact that we know that we're going to switch our zeros at our undefined points, if we look at the graphical representation of cotangent, we'll see that again, where we had zeros for tangent, we actually had asymptotes for cotangent. Where we had asymptotes for tangent, we actually have zeros for cotangent. And the nature of flipping the x and y has a nature of flipping these values. So cotangent goes in the opposite direction. Where tangent is a strictly increasing function, cotangent is a strictly decreasing function. And I know I didn't argue a lot of the details specifically for cotangent right there, but it's exactly the same logic as tangent. And I think the most important thing for both of these is you understand their basic nature. Tangent, because it's one of the first three trig functions, is more important than cotangent in my point of view, knowing the graph. But if you know the graph of tangent, it's easy to use that to generate the graph of cotangent. Importantly here, we have the periods are the same of pi. We're going to swap the domain here. So the domain in this case, instead of being based on these odd multiples of pi over 2, it's these multiples of pi. So we have all real numbers, importantly, except for these asymptotes, except for multiples of pi. And as with tangent, cotangent has a range of all real numbers. Again, just a quick recap of these two graphical representations. We consider the first period. When we graph a period of tangent, we want to include the x value, the input value of 0. So we go from negative pi over 2 to pi over 2. That gives us a period of pi. It goes through 0 at x equals 0, and then has this increasing behavior between these asymptotes. For cotangent, our first period that we talk about goes from 0, to pi, where we have these asymptotes. We go through 0 at pi over 2, where we had an asymptote over here, and we have this decreasing nature for the function.